Okay, set up right here, two different strings. So it goes from A to B, and at the middle, in equilibrium, it's 1.5. So that's what I want to show. So put that in the middle, like so. Let's put the tensions in there. That tension there, tension equals lambda x over L, and this way tension equals lambda x over lambda times the extension over L. Let's call that TA and TB, and I suppose I should put this on a table. Let's put the weight in straight down. That's 1.2 G, and obviously R going straight up, even though I haven't got the surface in there, but it's still in there. Right, and we've got to show this an equilibrium at 1.5. So let's show that TA equals lambda, and lambda for this one is 180, so it's 180 times by the extension. Well, I haven't put that in, let's put that in there. That's 1, and the extension here is 0.5, and this one here is 1.2 natural length, and then we got 0.3. So we've got TA equals lambda, and the extension is times by 0.5 all over L, which is 1, and that equals 90, and TB is lambda x, so lambda in this case is 360 times by the extension, which is 0.3, divided by lambda, which is 1.2, and that also equals 90, and so TA equals TB. That's in center at 1.5 meters, therefore equilibrium. And that does the first part. And now it's part I, and now part II. Okay, so now I've got to show that it's hit with speed u. I've got to show that the period is 0.314. So I need to get an equation with x double dot is minus n squared x. That's what I'm looking for. I'll try to draw that directly underneath the previous diagram. So that's my diagram. Obviously I've got my tension going back here, and I've got tension there, and we'll call that again TA and TB. We'll put the weight on here, 1.2 G. I'm actually going to miss off R. I don't need R in this case, I'm going to miss it off. I hope you don't mind. So we got distances. That's 1, and it's going to go another 0.5 is in equilibrium, and then we're going to take it x beyond there. As soon as I do that, that means I'm defining the right to be positive, and so that will be x double dot, the acceleration to the right. On this one here, we've got 1.2, and then we've got the bit in here with 0.3 beside them. That'll be 0.3 minus x, and now we can do it. We can now resolve in the direction of the acceleration. That's the way I'd go. And so resultant force equals mass times acceleration. I've got TB minus TA equals the mass, which is 1.2, times the acceleration, which is x double dot. And I need to work out what TA is, and we know that that is going to be lambda x over L. So lambda is still 180, and my extension now is 0.5 plus 0.5 plus x, and I have to divide it by my natural length for the left hand strip. I'm going the wrong way. Schoolboy error. I'm actually going to TB and to use TA, so I can get rid of that a little bit. I'll start that bit again. TB is this one here. It is lambda x over L. So lambda is 360 times by the extension, and the extension is 1.2 there. It's 0.3 minus x. 0.3 minus x. and it's over the natural length 1.2. Let's done that one, and then minus the TA bit. This is the bit I was working out before. Lambda for that one is 180 times by the extension, which extension is from the natural length, so it's a 0.5 and then the x, so that's 0.5 plus x, and that's all over the natural length, which is 1, and that equals 1.2 x double dot. And if I work that out, I'll come right up the page up here. That gives me 90 minus 300x minus 90 minus 180x equals 1.2x double dot, and that will give me the 90 and minus 90. That's always going to cancel out, so if you take it around the equilibrium, and that gives me minus 480x equals 1.2x double dot. So x double dot equals minus 400x. That's my n squared. Therefore, n equals 20, and the period, which is 2 pi over n, equals 2 pi over 20, which equals pi over 10, which approximately equals 0.314. And that now has done the second part, and I've now got to do the third part. I'll do it in a different colour, so otherwise it can get difficult. So 3, I've got to show that u is less than or equal to 6, and it goes with the simple harmonic motion. It cannot go too far. If it goes this way, it starts off. If it goes all the way across and goes beyond this 1.2, then it won't get simple harmonic motion, because this string will go slack and it will just bounce. So we've got to have the greatest amplitude it can go is 0.3. So the max, so amplitude has got to be less than or equal to 0.3 meters. And what I'm going to do is I'm going to look at the energy. So I'm going to look at the total initial energy, and I'm going to say that that's going to equal the total final energy. Well, it does. And the maximum final energy could be is if it's right across to here and it's not moving. So if it's moving at this point here, then it's going to go, it'll go beyond the 1.2, and it won't be simple harmonic motion. So, and the right hand string won't be stretched. The only thing we'll get is the elastic potential energy on the left hand side. So that this bit will have to equal the elastic potential energy of A, and that's all it's going to be, and that's lambda x squared over 2L. So on the left hand side we'll have the elastic potential energy at the beginning of A plus the elastic potential energy of B, plus we've been given a velocity, so I have kinetic energy to start with. As always, I always like writing down the formula. So lambda x squared over 2L, and let's work it out. So of A, at the beginning, lambda is 180 times by the extension is 0.5 squared all over 2L, which is 2. I've got to add on to that elastic potential energy of B, which is 360 times by the extension, which is 0.3 squared, don't forget the squared, over 2L, so that's 2 times 1.2, and plus, I forgot to write the formula for this, half mv squared, so it's a half times the mass, which is 1.2 times by v squared, and I'm going to make v squared be the maximum velocity it could be, and that's got to equal lambda of the left hand string, which is 180, times by the extension of that, where it's gone 0.5, it's got another 0.3 to go, so that'll be 0.8 squared all over 2. And if I multiply this out, that gives me 22.5 plus 13.5 plus 0.6 v squared equals 57.6, and that eventually gives me v squared equals 36, and so v equals 6 meters per second, and that's the maximum velocity, and that'll do. Part 4, a couple of ways of doing part 4. So I would use here x equals, we know it's given a use 6, it will actually get there, so it tells us the amplitude is 0.3, so x equals 0.3. It's released from the centre, so it's sine, or started from the centre, sine 20t. In this case here we want to be, so it's 1.3 meters from A for the first time, so it starts here, goes all the way across here and then back, so the x will actually be negative 0.2, so negative 0.2 equals 0.3 sine 20t, so sine 20t equals minus 0.6 recurring, so 20t equals sine to the minus 1 of minus 0.6 recurring, so 20t equals minus 0.729727. Well, obviously that's going to be negative, so that's where it would have started before. So or we also get, for sine it's 180 minus, so in this case it's pi minus this bit, so negative 0.729727. Can't be that one, and this one here, that will give me that t equals pi plus that over 20, which is 0.193566. And that gives a time. The other way you could have done it, you could have thought, I'll do it in green, you could have thought, okay, that's my projection onto the unit circle. It starts at this point here, so let's assume it starts here. I'll highlight it actually. It goes all the way around here until it gets to minus 0.2 there, and I have to work out what fraction of the whole circle that is. So I need to work out that angle there, which is obviously pi plus this little bit here, so I'll call it the whole big angle theta. So you will do theta over 2 pi, and that is the proportion of the whole revolution it goes, and so times that by the period, and the period we worked out earlier was 0.314, and that will give the same answer if you wanted to do it that way, but that's probably the easiest way here. And that's question 7 done.